The name of this video is Infinite Line Revisited. That is, revisited square. In fact, in this video, we are going to consider one more time, the third time in this course, the problem of an infinite line of charge with a uniform charge distribution with constant density lambda. We already solved this problem in two different ways. So let me sketch in a very small corner here the problem at hand. So we are considering again an infinite line of charge. I remind you that in a previous video we solved this problem considering a Gaussian surface of this type, a cylinder, which we called capital sigma, which had a central axis, the line itself, which again is characterized by a constant linear density lambda. This surface, we called it capital sigma. This was our Gaussian surface. Okay, to solve this problem, we want to find, as always, the electrostatic field at any point, at any observation point capital P in space. We choose, again, a cylindrical coordinate system. For example, this would be our r-axis. This is the origin of the system. This is our z-axis, and the angle var phi, we measured it in this fashion. This is our origin here, and we want to compute, to find the electrostatic field at any point capital P in space. We know that, in general, the electrostatic field E at any point capital P in space is comprised of three components. The three components with respect to this cylindrical coordinate system are the radial component ER, the var phi component ER phi, and the vertical component EZ. Once again, we suppose that we know absolutely nothing about these three components. We have no knowledge whatsoever. In a previous video, we were able to use symmetry arguments as well as, at the very end, Gauss's theorem in order to solve this problem, and we found that E var phi and Ez are 0, and Er is lambda over 2 pi epsilon naught r in the r direction. We want to start again from absolutely zero knowledge. In particular, we want to criticize these concept of symmetries. We want to verify if they make sense or not. In fact, perhaps I don't want to trust the symmetry arguments. They are a very qualitative argument. So what is the actual physics behind the symmetry arguments which we used in the previous problem? Note that they are not wrong. I'm just trying to criticize them in order to understand better what actually they mean and what kind of physical information they encode. And as it turns out, the physical information encoded by the symmetry argument is in the irrotational property of the electrostatic field. The irrotational property is nothing but Maxwell's equation, one of the two Maxwell's equations for the electrostatic field. We need to use it, and in fact, it's nothing but the symmetry arguments. They are encoded. These two pieces of information are equivalent to each other. It's just that the rotational property is more physical. It's actually more mathematical, so it makes sense to understand that in detail. Okay, so since we have absolutely zero knowledge of this electrostatic field, perhaps you can have a var phi and a z component as well. So we use now, this time, we begin with Gauss's theorem. So we use Gauss's theorem for the Gaussian surface capital sigma. TH is for theorem for the Gaussian surface capital sigma. When we do so, we know that Gauss's theorem is absolutely blind, is totally blind to E bar phi and Ez, at least on the lateral surface of the cylinder. if you look at one of the notes in a previous video, I also mentioned that we cannot use Gauss's theorem on the two bases, capital sigma 1 and 2, that's the way we called them in a previous video. However, in this video, I will relax this condition for a minute, because I want to make a bigger point. You can actually show what I'm about to say properly, but I'm not going to do it here. So we will disregard the effect of Ez on these two bases, capital sigma 1 and 2. On the lateral surface of this cylinder, we know that Gauss's theorem is blind to Ibar phi and Ez, so they cancel out in Gauss's theorem. And if again we disregard for a minute what happens to Ez on the two bases, capital sigma 1 and 2, we are able to find, by means of Gauss's theorem, that the only left component, the only component we can find with Gauss's theorem, is the only one we can actually find is ER, which is equal to lambda over 2 pi epsilon naught r in the radial direction. We found this already in the previous problem. Okay, so suppose that we use Gauss's theorem for the Gaussian surface capital sigma, we find this ER, and Gauss's theorem was blind to Ibar phi and Ez, so we cannot tell anything about them. But let's say that we trust that at least this piece of knowledge is correct. Okay. Now, what we want to do, we want to tackle one of these two other components, either the Ibar phi or the Z components. And for example, let us focus here on the Ibar phi component. Okay. So let's consider only the Ibar phi component. And instead of using symmetry arguments, I want to use the rotational property of E to understand that, to verify that phi is actually equal to 0, which is the same information we gained from symmetry arguments. With only this piece of knowledge, which we somehow obtained from Gauss's theorem with the caveats I just explained. All right. So how do we proceed? The way we proceed is as follows. We look at this line, and we look at this line from above in this fashion. So if I look at it like this, the trace which this line leaves on this board is just a dot. So let me now sketch this nicely in this region here. Okay, so this one is a circle centered around the trace of the line which I see on this board in this fashion. Okay. All right. Now, what we want to do, we want to make use of the rotational property of the electrostatic field, which tells us that the line integral, the circulation along any closed line gamma of E dot T dl has to be equal to 0. So this has to be true for any closed line gamma in space for the electrostatic field. So for example, we can use the following line. We start from a point A here. We go all the way to the trace left by the line along the radius. Then from this point, we go along the radius again. So this is the direction we follow. We go to a point capital B down here in this direction. Then we follow this circle for a little arc like this, okay, until this point capital C. Then radially, so we follow the circle, the arc in this direction. Then we go back in this direction to the trace. Then we go in this direction to one last point, capital D on the circle, and then we follow the circle to close the line back to A in this direction. This is quite an interesting line. So we go from A to the center, which we call O, then down to B, then we go to C in this direction, then we go back to O, then to D, and then to A. So this complicated line, which goes to this point, actually is still a well-defined line. I can use it. And it is a closed line. The whole structure is a closed line. This integral on this line has to be 0. And this line, we call it gamma bar phi prime. Okay, gamma bar phi prime. We will need two lines. This is the first line that we're going to encounter in this problem. So to solve this problem, we need to choose a cylindrical coordinate system, the same as here. So for example, this will be our r-axis. This is our bar phi axis, and bar phi starts from 0 right at this point. And the z-axis, I'm not going to sketch it, coincides with this point here. Okay, so it's the line itself, which I see, this is the trace of the line. Okay, and the origin, of course, coincides with that point. And note that the radius of this big circle, we call it capital R. Let's further hypothesize that the aperture of these two arcs, so this angle here and this angle here, they are both infinitesimally small, so they are both d var phi. So let's call this angle here d var phi, and this one is also d var phi. So let me put a nice cross like this. So these two angles with the cross are d var phi, the same. Okay, so now you write it there. Okay, so with respect to this cylindrical coordinate system, we define this angle here from this point to this point, bar phi 1, whereas this angle here from this point to this point, we call it var phi 2. All right, so this is var phi 1 and this is var phi 2. Great. So now we know all our angles here. A, O, O, B, B, C, C, O, O, D, D, A is the line. Straight lines, 4 straight lines, A, O, O, B, C, O, and O, D, and 2 arcs, B, C, and B, A in these directions. Okay, so we have our coordinate system, we have our angles, we have our radius. This we call it gamma bar phi prime. I think we are in a good shape to move on with the next part of the problem. So what is the next part of the problem? We want to calculate this integral up here, this circulation. Okay, and this circulation again, let's begin with this circulation. With this has to be true for any line. So let's begin with gamma bar phi prime. Okay, this has to be equal to 0. And again, this is our closed line. So this line again comprises 4 segments and 2 arcs. So we can rewrite this line integral as the integral along the segment AO, then OB. The integrand is the same, so I'm not going to rewrite it for simplicity of notation. Then let's keep the arc for a second, CO. Then we go from O to D. And then let's put together here plus aside the 2 arcs, which are BC arc plus the arc BA in these directions. 4 plus 2, 6. These are the 6 terms, the 6 components of this integral, okay? Now, let us begin to solve this integral here. This can be solved by means of our knowledge on ER, okay, which I calculated with Gauss's theorem. In fact, in these radial directions, the only component that can contribute to the circulation, to the line integral, is the R component, because this is normal, and var phi is also normal to the unit vector, which is radial. So UR dot UR is 1, and that's the only one which can contribute to all these 4 integrals. All right, so how do we write this? Well, this integral down here becomes, so the first integral here, this integral, let's call it 1, this integral 1 becomes lambda divided by 2 pi epsilon naught. These are constants of integration. Then we want to open a parenthesis here and we do the integral. Well, let's represent this integral from A to O with respect to the cylindrical coordinate system. So I'm going from A to O, which means I'm going from capital R to 0, the origin. Then we have our direction, well, we have 1 over R. The direction is UR. We need to dot this. The typical problem that I also always do, and so I will remind you now what the problem is. So we are going from A to O, so which means you may be tempted to write minus dr here as the infinitesimal element dl. So we're looking at the dl somewhere here on this axis. Since it goes in that direction, we're moving in that direction towards the center, you may think that this one should be minus. But remember that we go from large to small, from capital R to 0, so the minus is already encoded in the limits of integration, so we should not repeat the minus 2 times, so we keep it plus, because the minus is already built in here with respect to this cylindrical coordinate system, and so that's what we get for the first integral. And the rest is very similar, so we're going to get, similarly, the integral from 0 to r of 1 over r dr, I write it down dot product here, and similarly from r to 0, and again, so r to 0, r to 0, 0r, and again 0r. Okay, here there is unfortunately a major problem. The major problem is that we are going all the way to 0, and the integrand diverges at 0. So again, note that we are considering any point here on this line where we have our, apologize, this should look like this. So this is our field E, which is along R, along the R direction, pointing outward at any point, capital P, this point on the line A to O. Okay. All right, so this is our point here. This point here is PAO. Okay. So, with this in mind, what we need to do now, we need to understand what's going on with this integrand which diverges at 0. So this is obviously a major problem because this should diverges at 0. So this is an improper integral, okay? So we are dealing with an improper integral. What do we do when we are dealing with an improper integral? We can actually solve the problem by using Cauchy's principal value. How does it work, Cauchy principal value? Which again we use whenever we are dealing with improper integrals. This is improper because it diverges at 0. Okay? So we surgically remove an infinitesimal neighborhood around the point O with diameter here. Let's call this diameter small delta. And so what we do, we take the limit for small delta, which goes to 0 plus, because of course eventually we want to recover the entire line, so we need to go in this limit, of lambda divided by 2 pi epsilon naught, which is this quantity here. Now here we can start to sum up two of them together, 2 by 2. So R0 and R0, which means we get the 2 times the integral from R. 0 becomes delta, that's the way we do Cauchy principal value, of 1 over R dr. So now we accounted for this as well as this, transforming this 0 to delta in both of them. Similarly, for the other two integrals, we get plus 2 times the integral from delta to capital R of 1 over R dr. Okay, this is quite nice, because now, if what we can do here, we can simply swap the limits of integration here. So this becomes R, this becomes delta, this becomes a minus, and we end up having 2 times minus 2 times the integral from R to delta from R to delta. So these two integrals cancel out, and the result of this limit, even before doing the limit, we got rid of this singularity, and we get at 0. You would get the same result if you first solve the integral with delta. It will give you natural logarithms. The natural logarithms will cancel out even before doing the limit. So obviously this Cauchy principal value exists, is 0, and that's the result of this integral. So even though in the circulation we crossed the source, the charge source of this electrostatic field, yet it's not a problem because we can use Cauchy's principal value here, which is quite an important and powerful result, which actually comes about in many different points in physics, many different topics. All right, so now we took care of this integral here, so this whole integral is 0. What about this integral here? So this integral, this let's call it 2. Now we need to compute this other part. So I have more space, so let's start here. Okay, so how do we do that? Now this is quite important, as it turns out. So we are dealing with the two arcs, BC and DA. What field do we have there? Well, even if there is an ER component, does not contribute to the integral, to the line integral, because R is normal to U phi, which is the direction on these arcs. Similarly, it's Z. So the only component that can contribute for the line integral, in this case, for these two line integrals, has to be obviously a phi component, a var phi component. Okay, so let's sketch this var phi. We have no knowledge whatsoever about the var phi. So I can hypothesize anything I want about this var phi. And in particular, what I do, I pick this point here. So this point, I call it a point capital P on the arc BC, and this point here I call it capital P on the arc DA. So I pick these 2 points, and I hypothesize arbitrarily that, for example, here the tangent field in the phi direction is this huge field. I don't know anything about it. So this is E var phi a point capital P BC. Whereas here I choose, for example, a much more modest E, which again I hypothesize E var phi at this point P dA. Note that I have chosen on purpose, because I can do whatever I want, the magnitude of these two vectors to be completely different to each other. This could be 100, this could be 5. In addition, this vector points in the opposite direction of var phi, whereas this points in the same direction of var phi. So not only they have different amplitude, but also different sign. And you need to keep this in mind when now you want to find these integrals with respect to this coordinate system. We need to keep in mind that this, from my choice, from my own choice, I arbitrarily chosen it to be negative with respect to this cylindrical coordinate system. So we need to remember that minus sign. Okay, so how do we proceed to solve these two integrals? Now that we know this, there is another piece of information that we need to hypothesize here. So the other piece of information we hypothesize is that these E var phi's at these 2 points on the arcs, they are on an infinitesimal arc, on a DL, because they stem from an infinitesimal aperture d phi. So these quantities are infinitesimally long, okay? Because of that, I can hypothesize that over the entire length of this infinitesimal object, this field is the same at each point on this length, okay? So the hypothesis is that, for example, E var phi at point P BC is equal for each point on the arc BC. Okay, so that's the hypothesis. Same for E var phi at point P dA. And again, this is true because I'm assuming infinitesimal elements. Okay, we'll come back to this in an appendix. Now, with that in mind, we can take out the magnitude of these vector fields in the integrals because we don't have to integrate them because they are constant over these arcs. Okay, so these two integrals, 2, then become E var phi at point P BC. Now, as I said before, E var phi at point P BC, is it positive or negative? With respect to this coordinate system, points against var phi, so it has to be minus E var phi at PBC. Then we integrate. We can take it outside the sign of the integral again because it's constant. We integrate from B to C, and so we are going, in terms of angles, from var phi 1 plus d var phi, which is point B, this plus this, back to var phi 1. Okay. And so what are we integrating here? The direction of this vector field, which is u var phi, and we need to dot it with dl, which in this case has direction u var phi times capital R d var phi. Note again that, is worth noting again here, that this quantity here, it's positive Why is that? Because again, we are going from a larger value to a smaller value here of the angle, okay? So the fact that we are going against our phi is built in the limits of integration one more time, so I don't have to put a minus sign here, otherwise I would double count the minus sign. Okay. Similarly, for E var phi at PDA, now we are going in the same direction of var phi, okay? And we're going from small to large, so in this case, and note that E var phi at PDA goes in the same direction of var phi, therefore, we don't have a minus sign, we have a plus sign. It's constant on that infinitesimal arc, so it's E var phi at PDA, all right? And then we integrate between var phi 2 and var phi 2 plus d var phi. And what do we integrate? U var phi dot U var phi, so this is the direction of d var phi, times R, the infinitesimal element d var phi, in this fashion. All right. So obviously u var phi dot d var phi is 1, and so we need to do simply this integration between these two angles, which is rather simple considering we're integrating over d var phi. And so what we obtain at the end of the day, so here we obtain phi 1 minus d var phi. These two cancel, so it's minus d var phi when we integrate. Minus minus is plus, so we obtain a plus e var phi p bc, okay, times the result of the integral is nothing but d var phi times the radius r. What about this one here? Well, we integrate and we obtain phi var phi 2 plus d var phi minus var phi 2. These two cancel, so we have plus d var phi. So we obtain a plus e var phi at p dA, okay, in this fashion, times d var phi r. This has to be equal to 0, okay, because already this is equal to 0, so this sum has to be equal to 0. We can thus cancel these two quantities. And what we obtain here is simply that E var phi at point capital P BC has to be equal to minus E var phi at point capital P dA. Okay, so this is the condition we find from the rotational property of the electrostatic field. What does this condition tell us? Something very important. It tells us that, as it turns out, from this condition, we cannot, because of these rotational properties, of course, originally I arbitrarily chosen these two fields to be different magnitude, different sign, opposite sign. But then we need to impose some physics. We are imposing physics, so we find extra constraints on this, which cannot be arbitrary. The magnitude has to be the same, and the sign has to be the same, because I hypothesize these to be opposite of each other, but they pick up a minus sign, so they need to point in the same direction with the same magnitude. So for example, this cannot be. It could be something like that. We don't know yet anything about the size of this field, so I can choose either the big one and the big one here, or the small one and the small one, as long as they are the same in the same direction. So same magnitude, same direction, same direction. And once again, I could have chosen equivalently this magnitude, and here this magnitude, and this direction, and this direction, because this physics does not tell us how big the magnitude is, only that it has to be the same in the same direction. All right, so now that we have this condition in hand, E var phi at PBC equal minus E var phi at PDA, so we know that this vector field have to be the same at each point on a circle like this one, and let's call this circle here, this line, this oriented line, we call it gamma var phi double prime, to distinguish it from gamma var phi prime here. So gamma var phi double prime is the entire circle with radius capital R. At each point around this condition has to be true. Why is that? Because, and that's the very reason why I chosen this line gamma var phi prime in this fashion, to have these two wedges, because I can rotate these two wedges wherever I want to by an arbitrary angle, and the angle I can arbitrarily choose is basically the difference between var phi 2 and var phi 1. So this angle here, this angle, let's call it var phi delta, is arbitrary. So I can shift these wedges wherever I want to span each and every point on this line gamma over phi 2 prime. So this has to be true for each point P on any line of the type gamma over phi 2 double prime. Okay, it has to be true for any of those points due to the arbitrariness var phi delta, this difference of angles. Again, I can move them around to span the entire line here. Note that if I were to choose another line with a larger radius, let's call it capital R prime, then we can do the same argument. Of course, the field E bar phi there, from this property, we cannot tell whether this field has to be the same as this field, but yet on any line which has center in O, this condition has to be true for any point of any such line. So that's what we learn here. So in other words, we regain the same kind of information we had from the rotation symmetry about the line of charge itself. So the rotational property of the electrostatic field, in this case, for this specific structure, is equivalent to the rotation about the gamma axis. Isn't that beautiful? I think it's great. So now, really, we have a connection between a qualitative argument such as a symmetry argument, rotation, and the rotational property. This is equivalent. This condition is the same as rotation about the line of charge, which typically we call gamma. That's great. So this is our important result here. All right, so with that in mind, we are not done yet, because the only thing we were able to find, as in the case of the symmetry arguments, we were able to find that E bar phi, if it exists, has to be the same at each point on such a circle. Is it zero? Well, we need to do one more time, we need to use one more time the rotational property. In this case, we are going to use the rotational property, that is the circulation, this time about this line gamma bar phi double prime of E, the only component of course is E bar phi, dot TDL, okay? So in this case, E bar phi gain has to be constant, so the magnitude, we can take it outside the sign of integral, and so we obtain E bar phi. Here we can express this in this coordinate system, so we are going, with respect to this coordinate system, from 0 to 2 pi. T becomes, so we need to maintain, of course, the U bar phi from the field, dot it with U bar phi, times dl, which is capital R E bar phi. So this one, as always, gives us a 1. And so what we obtain here, we obtain nothing but 2 pi r, 2 pi capital R E bar phi. And this quantity is the rotational property. Here comes the physics, has to be equal to 0. So this implies that E bar phi has to be equal to 0. So we found this beautiful result that using one more time the rotational property about gamma bar phi double prime, it has to be true. This property has to be true for any line. So this is the new physics we enter. E bar phi has to be 0, which is really great. So we recovered entirely the knowledge we gained previously by means of symmetry arguments. In this case, using only the irrotational property of the electrostatic field. So symmetries are the irrotational property of the electrostatic field, nothing more than that. All right, so to summarize what we have done in this problem, we revisited one more time the infinite line of charge. We didn't trust symmetry arguments. Instead, we used Gauss's theorem blindly, getting ER, which we needed for the rest of the demonstration here, with the caveats I explained in the beginning. Then, instead of using rotation symmetries, for example, we use the rotational property for these two lines. One is this line here with the two wedges. We did the circulation of that, including this knowledge, and we found that the E bar phi has to be the same at each point on this line gamma bar phi double prime. That knowledge then, which recovers the rotation symmetry above the line, we use it again with one more rotational property to find that E bar phi has to be equal to 0. As an exercise, you can attempt to calculate, to do a similar argument. For example, in Piazza, you can think about a similar argument for EZ, which I didn't do here, okay? So I let you think about that. It's a little bit more complicated, and I prefer not to do it because this one is very elegant and very beautiful, and it gives a good sense of what's going on between symmetry arguments and the rotational property. To conclude, criticize, please, all my students. I want all my students, all the people learning with me this course, to criticize highly all the textbooks and literature which is out there about Gauss's theorem. It seems that there is only Gauss's theorem, and somehow symmetry arguments. You can do it, but at the very least you need to do the symmetry arguments as we've done in the previous video. Most importantly, you need to understand that the symmetry arguments are nothing but the rotational property of the electrostatic field. So criticize heavily all these textbooks which are out there. I think this is very important. Thank you.